As most of you know, that pressure vessels are usually designed in various shapes, and hence are supported in different structure shapes. So generally speaking, the main shapes are cylindrical and spherical pressure vessels. Regarding cylindrical pressure vessels, they include heat exchangers and condensers, and may be either vertical or horizontal. Cylindrical vertical vessels may be supported by one of the following: steel columns, cylindrical plate skirts, or plate lugs attached to the shell. Cylindrical horizontal pressure vessels, including heat exchangers, may be supported on one of the following: long concrete slabs, or on two or more separate foundations. Spherical vessels are usually supported by steel columns, welded to the shell and usually protected by coating and fireproofing.
Pressure equipment usually requires some form of support. Typical support arrangements include metallic or reinforced concrete structures on reinforced concrete foundations. Remember that structural components do not usually form a part of the pressure boundary, and hence are often designed in accordance with the applicable user standards or specifications. Nonetheless, supports may be critical in assuring the continued integrity of the pressure equipment, as failure can lead to improper support or uneven settlement that could ultimately cause a loss of pressure containment.
Foundations for pressure vessels are mostly constructed of two types of foundations. First type is steel reinforced concrete. Second type is structural steel fireproofed with concrete.
The foundations for equipment like heat exchangers and horizontal pressure vessels are usually consists of steel cradles, that is fixed to concrete piers. Steel cradle is commonly known as steel saddle support in industry. A typical exchange foundation is shown in this figure.
Pressure vessels shall be periodically inspected to assist in assuring safe operation until the next scheduled inspection. These inspections shall assess the condition of the pressure equipment for integrity and its fitness for service until the next scheduled inspection. At the pre-estimated design conditions and normal operational parameters. Inspection may be both internal or external, and may include supplementary non-destructive techniques, or pressure tests. The external inspection gathers information about the condition of external surfaces of pressure equipment, and as a minimum, includes inspection of the external components, as shown in this figure.
The inspection of foundations and structures will usually be carried out in conjunction with the external inspection of the pressure vessel.
The crevice formed between exchanger shell and a cradle support should be carefully checked. Moisture lying in the crevice can cause rapid attack on carbon steel and on low-chrome molybdenum steels. If the cradle is sealed with a mastic compound, this seal should be checked to make sure that it is intact. As a recommended practice, cradles are often seal welded to vessel shells to prevent moisture from accumulating in the crevice and causing corrosion.
All types of foundations shall be inspected for damages such as spalling, cracking, and settling.
There are several factors that causes cracking of the foundations, such as excessive heat, mechanical shock, corrosion of reinforcing steel, or the freezing of entrapped moisture. Inspection of this type of damage should consist of visual observation and scraping to reveal any hidden damages or corrosion. Measurements of the depth of such damage can usually be made with a straightedge or a steel rule.
As discussed earlier, the cracks in concrete or fireproofing may be caused by one or a combination of the following: excessive heat, poor design, poor material, mechanical shock, or unequal settlement. Inspection for cracks should be mostly visual, however some picking with a pointed scraper may be helpful. Very small openings or cracks in concrete or fireproofing that is caused by high temperature or temperature changes can usually be identified by their hair-like appearance. Such cracks are not usually serious, unless they expose the steel to corrosion. One of the most important questions arises. What should I do as an inspector when visually detect major cracks appear and propagate? And what are the diagnosis steps? Basically, there are three main steps to consider for this specific case. First step is to do the necessary measurements on the pressure vessel by conducting levels and dimensions survey. If the measurements indicates that no settlement has taken place, then the cracks are probably caused by thermal fatigue, poor foundation design, or poor material. The second step then is to perform a complete check or engineering study to investigate the foundation design. If such investigation shows that the design is correct, then the cracks are most likely caused by thermal fatigue or the use of poor quality concrete material. The third step then will be a careful visual examination with minor chipping with a hammer to check the extent of the cracks. However, removal of a core for testing is recommended to reveal the quality of the concrete material, or otherwise the thermal cyclic fatigue effect could be the root cause of the cracking. Coming back to the foundation settling, important question arises: what should we do if foundation settlement detected? Basically, some settling is expected in any foundation. Therefore, when settlement is even and of a nominal amount, no trouble should be experienced. However, if it is excessive or uneven, the settlement should be corrected before serious damage occurs. Unfortunately, a PI code neither specify a criteria for design parameters, nor for acceptance of the settling, and therefore engineering specialist consultation is recommended in such cases. Consequently, most users have established their own standards and recommended practices for this regards. Please remember, when foundation or support settlement occurs, the condition of connected pipelines should be checked immediately. This part will be discussed later in detail, in different chapter of this course.
Usually, a rough check for uneven settling can be made with a plumb line and steel rule, then observing the settlement by noting the misalignment of the foundation with the surrounding paving or ground. The frequency with which settlement measurements should be taken depends on the rate and the seriousness of the settlement. However, if accurate measurements are desired, then a surveyor's level may be used. In all cases, records of settlement should be maintained, particularly on vessels known to be settling.
Vessels supported on long concrete slabs, or on two or more separate foundations, are more likely to undergo uneven settlement.
Support for long horizontal vessels are often designed to allow movement between the vessel and supports. The absence of expected movement indications. For example, if there is wear on bearing surfaces, this may cause deflection in the support structures, and consequent further investigation.
Observation of the alignment of the pressure equipment and its associated pipework should be used as an indication of potential problems with foundations and structures.
Condition of anchor bolts cannot always be completely determined by visual inspection. The area of contact between the bolts and any concrete or steel should be scraped and closely examined for corrosion. In fact, this will not reveal the condition below the top surface of the base plate or lugs, and therefore a sidewise blow with a hammer may reveal some indication of any deterioration on the anchor bolt below the base plate.
A conventional method is to chip out a foundation underneath the anchor bolts to reveal the condition of anchor bolts below the base plate. These photos reveals the real condition of this anchor bolt after chipping out the foundation, and it is completely corroded and separated in two parts.
The nuts on anchor bolts should be inspected to determine whether they are properly tightened. Ultrasonic testing and phased array testing may also be used to examine anchor bolts without the need for damaging the foundation. This photo illustrates how the defective bolts would appear in the phased array scan. Basically, there are two types of anchor bolt failure. The first type is the distortion of anchor bolts due to serious foundation settlement. In such case, the anchor bolt will be under shear, then ruptured as shown in this photo. The second type is the damage due to corrosion or cracking mechanisms. An example of completely corroded anchor bolt and bracket can be seen in the second photo.